Hey everyone, so today we're going to be continuing with ketones and aldehydes and some specific reactions for them. So we'll be talking about specifically nucleophilic addition of ketones and aldehydes. We'll use some language like we did before when we're talking about the general mechanism for these processes, and then using language like oxidation and reduction when we're talking about adding or removing bonds to oxygen or hydrogen, because a lot of times with ketones and aldehydes, that's what you're going to be doing here. So what is the general mechanism for the reduction of an aldehyde or a ketone? So we'll draw ketones in general, but the mechanism is the same for both of them. The difference really just comes in terms of reactivity, and like we talked about before, if you try and oxidize a aldehyde, you'll get a carboxylic acid, whereas a ketone, you won't really get any reaction. So the general reaction, or the general mechanism, depends on a nucleophilic attack on the carbonyl carbon, right? And so if we look at our general structure for an aldehyde or a ketone, this right here is our carbonyl carbon, right? And so this carbon, we know, is sp2 hybridized, so it's going to all lie in the same plane. So I'm going to do a bad job probably here of drawing what this looks like. This is going to be going back into the page, and then this is coming out, but it all lies in the same plane. In the presence of a nucleophile, so the nucleophile, I think, is a blue color, usually has some lone pair to then attack this electrophilic carbon, because the oxygen is pulling a lot of electron density away from this. It's going to attack this carbon, and well, it's not extremely relevant. This attacks at about 75-degree angle is kind of what it comes on. That's kind of more important if we think about how things like sterics of these R groups will affect the reaction, right? So it attacks this carbonyl carbon, and then the bonds from this pi bond between the carbon and the oxygen then move up to the oxygen here. And the oxygen already has two lone pairs on it, and that's going to create an alkoxide intermediate. So that'll look something like this. And we have our nucleophile now. That's at about a 75-degree bond angle, and this is also going to be a tetrahedral, or now sp3 hybridized intermediate, right? Because now we have three bonding pairs for this carbon atom, so it's going to be sp3 hybridized. And I'll draw the dashes out for this particular mechanism. The stereochemistry isn't could be that important, but it is good to keep in mind all this, right? So this is called our alkoxide ion, right? And this is an sp3 carbon intermediate. And then, depending on the conditions that we have, so let's say that we have acidic conditions, where, most of the time we can do this either in basic or acidic conditions. So we add H3O plus in this solution. Well, then the H3O plus is going to protonate the alkoxide ion and then generate water as a byproduct. And so what we end up with is a tetrahedral alcohol in this case, right? And so this can create a number of different types of molecules. For example, if we're looking at carbohydrates, this will create hemiacetals, which is going to have an ether right next to an alcohol group. Or the other, if you have a cyanide group there, they're called cyanohydrins. Or you can have diols, is a lot of times what you'll see them create as well. And so then we get, wrong color. We get our nucleophilic, our nucleophile bonded down here, right? So this is a general mechanism for how the nucleophilic addition of a ketone or aldehyde works, right? So I put two R groups here because it can be an aldehyde or a ketone, but this works for both. So this works for both ketones and aldehydes. And so as you can imagine, this is going to depend a lot on the type of nucleophile that we have, right? So these reactions depend on nucleophile, right? So these are two different classes. We have our charged nucleophiles, negatively charged, and also our neutral nucleophiles. So both of these are going to work. You can imagine that this is just going to change the mechanism slightly depending on which group of nucleophiles. So in the last one, the mechanism that we just did, that example was using a negatively charged nucleophile, right? And that's why we need the presence of acid or water or something to come in and then protonate the alkoxide ion. And so if we look at something like water, that's a neutral nucleophile. We can have an alcohol and an amine, ammonia. Those are all some neutral nucleophiles. And really those are going to work in the same essence. The difference is that this nucleophile is also going to be protonating this, protonating the alkoxide ion. And when it does that, it's then also going to lead to a dehydration that's going to end up happening. Both of these are both going to work for aldehydes and ketones. We just draw the two R groups because that second R group, even though technically hydrogen is not an R group, we can label it that way. And so, for example, if we have the same ketone or aldehyde, we can then split off this reaction into two different types of mechanisms. One is going to be with the the neutral nucleophiles, and the other one is going to be with the negatively charged nucleophile. So the negatively charged nucleophile, we can show, is going to give some sort of alcohol with the nucleophile bond, and what happens with the neutral nucleophiles is eventually you'll get a double bond to whatever that nucleophile is. And so in both these cases, let's say we have our nucleophile, it's a neutral nucleophile, so it has two hydrogens bonded to it. The neutral nucleophiles usually have an extra proton there that it's carrying with it. And then the negatively charged nucleophile up here, both of these are going to be attacking the carbonyl carbon. And when they do that, the electrons from the pi bond between them then go on to the oxygen atom. We already have the two lone pairs here. And then this generates our intermediate, which is going to be the sp3 hybridized tetrahedral intermediate. I'm not going to draw the dashes and stuff on this one. So here we'll have the minus charge there, and then our nucleophile bonded. The only difference for the neutral nucleophile is now this is going to have a positive charge on it, and then two hydrogens here as well. But it still has the same shape or looking intermediate. However, because we have a positive charge here close to this negative charge, you will then get a rearrangement where this proton will move to neutralize the oxygen there, and then the electrons from the sigma bond between those, in this case the nucleophile, sorry, I should write, this is a nitrogen, although it could be, this is a nucleophile, then move on to that nucleophile. So you get a rearrangement of this intermediate, right? This is our alkoxide intermediate. This one you get a slight rearrangement of this intermediate to something like this, R prime and U H, right? So this is the two intermediates that we get. And then what we saw in the previous on the previous slide for the general mechanism is that if we have acid or water, then this will be neutralized and will generate our alcohol bonded to then the nucleophile OH. The next one, I'll continue on the next page. We usually go through another type of dehydration, which means we're going to lose water in this case. And so if we look at this molecule or the intermediate, where the intermediate ends up, and I'll redraw it so we can see nucleophile, lone pair, H, and OH, we can see that if we lose water, so we go through a dehydration reaction after this, which we'll be doing in lab this week, or actually next week we'll go through the dehydration. The first part is just the photoreduction. This, when we lose water, right, if we count all the different atoms that we have here, we have one hydrogen, another hydrogen, and O. And so this goes through a structural rearrangement that then gives us something like this, right? So we've replaced the oxygen in our aldehyde or ketone with whatever the nucleophile is. So that can be a nitrogen in some cases, or it can be an oxygen. Again, if it was water, that was our neutral nucleophile, or it can be an amine, right? So with an amine, you can imagine that can be a relatively complicated group. You can generate an alkene from that, right? So then this is our final product for the neutral nucleophiles. Oh, the general mechanisms for this are not too complicated. It's really the same idea. You get a nucleophilic attack of the electrophilic carbonyl carbon here, and then you're basically moving electrons on and off the oxygens, and then forming bonds with the nucleophile itself. And so we can ask, are aldehydes or ketones going to be more reactive? And so what affects stability? Well, things like sterics. We saw that in the aromatics chapter. The sterics, right? How bulky groups are can affect stability, right? So if something's bulky, it's going to be less stable to form a bond with that atom or molecule, because the sterics are going to basically strain the structure. And then the electronics can as well, right? So this would be things like resonance or hyperconjugation and induction, right? And so we can use these same ideas when we're looking at aldehydes or ketones. So let's say we draw an aldehyde, and then this will be an H3C. We'll just do a simple ethanal, right? Aldehyde right there, that'd be ethanal would be the name for it. And then we can compare that with a ketone, and we can just do 2-propanol, or propanone, sorry. So this would be 2-propanone. We don't really need the 2 there because it's a little redundant. But if we were to draw what we would anticipate the kind of electron density to be for both of these groups, we would see that, let's say I'll use blue for electron density, that these are going to be kind of bulky like that. It's going to kind of be similar here, and then there's going to be a lot of electron density around the oxygen there. And this is the same idea here, right? They're going to have a bulky part of the 2 methyl groups that are right there. And then maybe this side, since it's a really high electron density, you can make that even larger. Compared to the carbons, right? So it'd be red. So it's like a high electron density part of the map. And if we compare that to then the aldehyde, we see that we get similar over here on the methyl group over there, and then large electron density around the oxygen again. However, when we get to the hydrogen now, we have very little electron density around the hydrogen, right? And so this means that if we have a nucleophile, and I'll use, I should have stayed with blue, but I'll use green here. If we have a nucleophile that is then coming to attack this carbon, it's going to be a lot easier for this nucleophile to get in this case, right, on the left-hand side, because it doesn't have as much bulkiness, right? It has to come in at that 75-degree angle, and in where all, it's a trigonal planar or sp2 carbon, so it has to come in perpendicular to that plane, and that's going to be harder to do when you have the bulkiness of the two R groups that are there as well, right? Like these two R groups are basically adding to bulkiness to make it harder for the nucleophile to then come in and attack, right? So that's how the sterics are going to affect. The other thing we said is that we have the hyperconjugation effect, and so we can think about this. Again, we'll just take a second to review what the hyperconjugation was. If we have an aldehyde and H3C like this versus a ketone, CH3, so the same two ketones here, we know that there is a partial charge, positive charge on this carbon because the oxygen is pulling a lot of electron density away, right? So there's a partial negative on the oxygen in both of these cases. And so we can use the same analogy that we have with carbocations, right? That a 1 degree carbocation is less stable than a 2 degree carbocation. Carbocation stability, which is then less stable than a 3rd degree carbocation, right? And so these aren't full charges like you have with a carbocation, but the same principles can be applied to look at the stability here, right? So this partial positive charge can be stabilized, and in green here, I'll draw the p orbitals. Sorry, not the p orbitals, but the sharing or the kind of induction that happens from having a neighboring carbon atom versus a hydrogen, right? So the fact that in this molecule there's two methyl groups inductively stabilizing through hyperconjugation, which again is the delocalization through the sigma orbitals, inductively stabilizing the partial positive charge. And here, that doesn't happen with the hydrogen, it only happens with the methyl group. There's only one methyl group stabilizing the partial positive charge. Right? So because the aldehyde doesn't have that extra R group or carbon atom there, it's going to be less stable, right? And if it's less stable, that means it's going to be more reactive, right? So in general, the aldehydes are going to be more reactive than the ketones for this reason, because you have less stability of this partial positive charge, and also because of what we talked about before, which was the sterics, right? We have these bulkier groups that are on the carbonyl carbon, and that's going to make it harder for the nucleophile to then attack this partially positive electrophilic carbonyl carbon here. And then also, I also mentioned resonance. So one specific example of this is that we know that something like benzaldehyde, right, has these extra resonance structures. And because it has these extra resonance structures, that means that benzaldehyde is going to be I don't know why it keeps erasing, to be less reactive than something like cyclohexanal, right? So that looks something like this. Draw that better. something like this, right, where we don't have the aromatic ring there to then resonate with the carbonyl group there, and that means that it's not going to be as reactive when you have the aromatic ring there, because you don't have this stabilization from the resonance phenomenon, right? So whenever we think about reactivity, we're also thinking about what's going to be more stable. The more stable something is, the less reactive it's going to be, right? And we can also look at both these kind of colors on both of these structures here. Both of these, electron density maps here. The colors indicate how dense the electrons are there. It doesn't change the volume of it at all. It just gives you a different color, right? So this red here means that there's a lot of electron density here. And well, how easy it is for the nucleophile to come in and attack in each of these cases, right? We have the nucleophile. Depends on kind of the amount of blue in this electron density map, right? And so you see for something like formaldehyde, which is the non-aromatic aldehyde, it's going to be easier because there's more blue. It's going to be more positively charged or more electrophilic. It's going to be easier for the nucleophile to reach there. Where when we have the whole aromatic ring that we kind of share electron density with here, you can tell because there's a lot more green here. There's really only this small little blue area right here, right? That means that this electrophile isn't as good of an electrophile or it's not going to be as easily attacked by a nucleophile because it's more electron density is shared with this aromatic ring here. So aromatic aldehydes are going to be less reactive than the aliphatic, right? So this is, I should say, compared to aliphatic aldehydes. Okay, so that kind of concludes what I was going to talk about in terms of the reactivity of aldehydes and ketones and the general mechanism for the nucleophilic addition of these things, right? And so you can see you can change the nucleophile in a lot of these scenarios, but the general mechanism for how aldehydes and ketones react should be the same. Okay, so next time we'll talk more about specific reactions, so things like hydration, the addition of hydrogen cyanide, amines, and a little bit more specifics, and maybe some exceptions to what we've talked about today.